Hello everyone. In this video, we will continue to examine topic D.3 cosmology, and in particular, we will look at solving problems involving Z, R, and Hubble's law, and estimating the age of the universe by assuming a constant expansion rate. The first thing I'm going to note is that at the end of last section, I probably should have pointed out that there are a number of good questions that apply to sort of calculating quantities having to do with redshift, recessional speed, and using Hubble's law, and those can be found here and here. One problem, though, in particular, is so important that we're actually going to walk through it ourselves, and that is using Hubble's law to come up with an estimate of the age of the universe. So notice this isn't an exact calculation for reasons we'll discuss, but you can actually estimate when the Big Bang was from Hubble's law. So how? Well, you can estimate it from the Hubble's constant. Consider this. If you assume galaxies have been moving away from each other at a constant velocity, so the assumption we're making right now, which turns out not to be 100% accurate, is that this expansion is constant. It's been the same throughout history. Then they've been moving away from each other at a constant velocity equal to h naught times d. And if you consider that the time it takes for them to have gotten this far is equal to the distance they've gone divided by the velocity they're moving, then we can come up with an estimate for that total time by taking d, the distance, and dividing by the velocity. But because the velocity is related to the distance, if we take that distance d, divide by the velocity h naught d, then notice it doesn't matter what the particular galaxy is, how far away it is, we can get an estimate for the time of that particular travel just by inverting the Hubble constant. So we take the inverse of the Hubble constant. Now the problem is the Hubble constant is in some really, really rough units. It's in kilometers per second per megaparsec. Notice that there are two factors of length in there which cancel out. So that's really ugly, which means we need to convert that properly. So to do that, we're going to take h naught about equal to 67.7 kilometers per second per megaparsec and multiply by the number of megaparsecs per kilometer, or more accurately, divide by the number of kilometers per megaparsec. This cancels out our kilometers and our megaparsecs and gives us a value for h naught of 2.19 times 10 to the negative 18th per seconds. Okay? Then to get the total time, we just invert that. So we invert it. That gives us this value for the time in seconds. And if we convert that time in seconds to that time in years, we get an estimate of about 14.5 billion years, which is approximately our best understanding the age of the universe. Now, that value has changed over time slightly, and it really crucially depends on our value of h naught, which has been a source of some surprising conflict. It's one of the most hotly contested constants in history, actually. So there have been many measurements which disagree with each other, but the accepted value is somewhere between sort of 67 and 73. And this value stems from sort of a combination of the techniques of measuring it. This gives us this estimate of about 14.5 billion years, which is absolutely in the right ballpark for the rough age of the universe so far.